So, good evening, everyone. So, here we are for this problem solving session number 7 for the course Biointerface Engineering. So, this particular session is dedicated for solving the week 7 assignment. Similar questions to the week 7 assignment. The course instructor for this course is Dr. Lalit Mohan Pandey. He is the associate professor in the Department of Biosciences and Bioengineering, IIT Guwahati. I myself, I am Shilpa Nandi. I am the NPTEL PMRF TA for this course. I belong from the Center for the Environment, IIT Guwahati itself. So this is particularly a doubts and interaction session that occurs weekly. So every Tuesday from 7 to 9 p.m. So this is the second last live session for this particular semester. So if you have any query during the session, you can raise your hand, unmute yourself, and then raise the query. Or the questions can also be posted in the chat box. So, apart from this, there is a discussion forum for the course, which is available in the SWAM portal. So, you can post any of the questions or any of the queries related to the live session or even the course can be raised in that particular discussion forum. So those questions will be addressed in the forum at that time or even in the next week's live session. So the outline for this live session is, so we will first discuss the week 7 course content recap. We'll go through it. That is lecture number 19, that is surface modification. Lecture number 20, surface modification techniques. And lecture number 21, that is coating of calcium phosphates on titanium. So then we will, after going through the recap of the week 7 course content, we'll go through week 7 related assignment questions and answer discussion. So we'll solve certain questions which will help you in solving the questions of week 7 assignment that has been uploaded in the portal. Okay. So firstly, we will discuss about lecture number 19, that is surface modification. So as we studied in the last lecture about biomaterials and biocompatibility. So here we can see what are the various applications of biomaterials. So it involves like implantation in case of bone implantation, dental implantation. Then there is tissue engineering, drug delivery, as well as biosensors. So these particular biomaterials have properties that depend on the composition, that is chemical composition, and structure or the morphology, and the intended functions. So the functions would be so these particular composition and the structure of the biomaterial would be based on the intended function of the biomaterial. So apart from that, we also do various fabrication of biomaterials. So engineered biomaterials, that is metallic, ceramics or polymers, or we go for surface modifications to basically tune the biomaterial function or the desired function. Then these surface modification could be physical, chemical as well as biological in nature. So any biointerfacial interaction that it takes place at the outermost surface. So at the outermost surface of the cell, these biointerfacial interaction will take place. So between the body fluids and the biomaterial implant, firstly there will be a surface water interaction, then there will be a protein surface interaction, and lastly the cell surface interaction. So this particular interaction we already discussed in the previous week's session. However, we can just go through a quick recap of this as well. Okay, so why do we need this surface modification? So basically, these biomaterials are intended to interact with the biological systems. So the what we want is we we want the desired functions, right? So the material surface and not the bulk property that plays the role in the interaction. So it is the material surface and not the bulk property which plays the role in the interaction. So this material surface requires certain modification in order to work properly. So these interactions determine the host response towards the material respective to the application. So finally, whatever the material surface is, it will again determine the interaction and finally the host response towards the material. So what is the purpose or the role of these surface modification is? So it alters the surface properties to enhance the performance in the biological environment while retaining the bulk properties of the device. So basically we want to tune this biointerfacial interaction, or we want to tune the biomaterials functionality, right? As well as it increase the specificity of materials towards the particular cells. For example, this tuning, for example, sometimes we want the biomaterial to be very specific towards attachment, towards adhesion toward particular cells. So that's why we want certain surface modification. Another is to reduce the undesired adhesion or reactions. Apart from increasing the specificity, we also do not want any undesired or unfavorable adhesion, like unfavorable adhesion as in case of we do not want any pathogens or any microbes to get adhered to the surface that will hamper the functionality or hamper the interaction between the biomaterial and the cells. So what are these objectives of the surface modification? uh, to reduce the bacterial attachment or adhesion, as we saw that we do not want any undesired interaction. Then we can also regulate the protein adsorption, regulate the cell adhesion, then anti-fouling or surface cleaning. Right. So anti-fouling is basically the growth of these bacteria in the biomaterial surface. Then reduce the friction and wear. So we do not want these implants to cause any wear or tear in the cells, right? Lastly, corrosion or degradation resistance. So suppose in case of any bone implant, we do not want any corrosion. Otherwise, what will happen? It will lead to certain inflammation and again cause various diseases or various infections in the body. So bacterial adhesion is one of the significant problems in the field of biomaterials. So these basically occurs via the protein and polysaccharide in the cell wall. And this is a non-specific interaction. So the composition of these bacterial cell wall is, it is either gram positive or gram negative in nature. So these regulate the adhesion on the surface. So some surface receptors favors the plasma protein like fibrinogen, fibrin, fibronectin or vitronectin. And even pili that is present on the bacterial surface facilitate the initial surface attachment. So we do not want this bacterial adhesion in the biomaterial surface. So various traditional approaches are present of surface modification, like coating the surface with antimicrobial agents such as silver nanoparticles. So if we coat the surface of the biomaterial with various antimicrobial agents including silver nanoparticles, what will it do? It will not allow any microbe to get adhered to the surface of the biomaterial. Other than that, antibiotics can be used. So, or we can use cell wall disrupting agents which are cationic in nature. However, these traditional approaches comes with limitations. Like in case of if we use antibiotics, what can happen at, at a particular time or after a particular time, it will these microbes can again develop certain antibiotic resistance. Or if these usage of antimicrobial agents such as silver nanoparticles, sometimes these are hazardous and can release various other toxic particles in the body. So this again puts severe restriction on their use, right? So we move forward to various other surface modification approaches involving, firstly, it is application of positively charged surfaces. So we'll go through it one by one. So what are these positively charged surfaces? So if you coat various positively charged surfaces over the biomaterial, what will it result into? Various electrostatic interaction. So why do we want this electrostatic interactions particularly? Because what it does is like these electrostatic forces when present between the adhered cells and the surface, they impede the cell elongation and subsequent cell division. So uh, it won't allow the microbe to grow over the biomaterial, right? So the adhesive electrostatic bond weakens with increasing the ionic strength, and which is inevitable in most of the biological systems and other applications. So apart from this, microbes also produce various extracellular polymeric substances which will again interfere with this electrostatic interactions like biofilm, right? So these positively charged surfaces, with the help of their electrostatic interaction, helps in avoiding the adhesion of the various microbes onto the surface. Apart from this, we can go for low surface free energy coatings. So the Gibbs free energy, as you can see, of adhesion is given by gamma Cs minus gamma Cl minus gamma Sl. So this Cs is cell surface, Cl is cell ligand, and Sl is surface. Cl is cell liquid interface, and Sl is solid and liquid interface. So what do we want is we want it to be in a uh, 0, or we want it in the lower side, right? So the delta G should be lower, which will help in avoiding the adhesion. So adhesion is expected to decrease with the decreasing value of the surface energy of the substratum surface. However, hydrophobic surfaces also promotes adsorption and adhesion of the components from the solution and surface active substances. So hydrophilic surfaces, we want the surface to be hydrophobic in nature instead of hydrophilic, right? Apart from these low surface free energy coatings, we can also go for polymer brush coatings. So what we can do is we can graft various soluble polymers like polyethylene oxide, that is PEO, at one end onto the substrate surface and leave the other part dangling in the solution. So these polymer brush coatings have different orientation, as it can be in mushroom orientation or brush orientation. So in case of mushroom orientation, you can see the distance between the two polymer brush is more, whereas in case of brush like polymer coatings, the distance is less. So the density of the polymer, or the grafting density of the polymer, determines the deposition of the cells onto the surface. So if the grafting density of the polymer increases, there will be a decrease in the deposition of the cells. And if the grafting density of the polymer decreases, there will be a increase in the deposition of the cells. So what we want is, we want a higher grafting density of the polymer, right? Moving on, to regulate the protein absorption, what basically is the idea behind it is to reduce the undesirable or uncontrolled responses to these implants and devices. These surface modification also we already discussed in the previous lecture, that is lecture 17 and 18. So these various surface modification helps to reduce the non-specific adsorption, as well as again, as I said, that we want the surface to be hydrophobic in nature instead of hydrophilic surface. So hydrated hydrophilic surface like PEO reduce the protein adsorption. Also, the coatings of polymers, ceramics, or self-assembled monolayers and biomacromolecules also help in modifying the surfaces. So we'll discuss one by one what are these surface modifications in the next in the coming PP present in the coming slides. So how can we regulate this cell adhesion? What is the idea behind this cell regulating the cell adhesion? So biomaterial requires to regulate the cell adhesion for the application purpose. So in case of bone implants, like osteoblast cells need to integrate with the implant for the growth. And in case of biomedical sutures or pacemakers, cell adhesion is limited via the cell modification. So what we need to do is we want to prepare various biomimicry surface. Biomimic surface as in a surface, a biomaterial surface that functions, that has various biological functions. So as you see, hydrophilic surfaces resist protein adsorption, whereas hydrophobic surfaces favors the protein adsorption. And if you use various surface coated with heparin, it acts as an anti-thrombogenic surfaces. Various if and other in other cases, like if any surface is coated with albumin, it can act as in resisting the platelet adhesion. So if the surface is again coated with fibronectin or collagen, it promotes the cell adhesion. Similarly, if we coat the surface with hydroxyapatite, it promotes the bone cell adhesion. So usually in case of bone implants, how do we do the surface modification? We try to coat the surface with hydroxyapatite, right? So anti-fouling or surface cleaning. So anti-fouling, in case of when bacteria grows over this biomaterial, it can lead to anti-fouling, right? So if we have a super hydrophilic surface, so what happens if any contaminant is there, the water goes beneath the contaminant. But how if we have a super hydrophobic surface, what will it do is the water will pick up the contaminant. So usually we want a super hydrophobic surface is basically favored in case of uh, if we want to have a surface cleaning property. So oil, grease and other particulates and biological contaminants gets removed if we have a super hydrophobic surface, right? So again, to reduce the friction and wear, what why do we want to reduce the friction and wear? For example, in case of bone and joint implants, what we want is we want high lubricity. So in this case, we want to have minimum frictions and wear inside the body, right? So how can we achieve that? We can use various hydrophilic modification of the surface. What will it do? It will increase the liquid on the implant surface and which can act as the synovial fluids. Other than that, we can coat various polymers or hydrogels and proteins over the biomaterial. So in vivo applications, lubricant surface tends to exert low stress on the surrounding tissue. So depending upon the function of the biomaterial, for example, in case of bone and joint implants, we want to reduce the friction and wear. Similarly, resisting the corrosion and degradation. So again, depending upon the function of the implants, we do not want the implant to degrade as soon as it enters the body, right? So what we want is we want degradation resistance. How can we achieve a higher how can we achieve this degradation or corrosion? So again, surface modification will help to regulate the degradation, and again it will help improving the resistance to corrosion. So addition of an inert layer over these biomaterial surface help to decrease the degradation. So why don't we want these degradation is because a higher rate of degradation of the biomaterial in the body may start again the immune response. So we do not want any inflammation. Okay. So these physiochemical properties of the surface like surface chemistry, wettability, surface potential, surface roughness and surface texture are taken into account when we are going for this biomaterial surface modification. So how can we modify these surfaces? We can go for gradient coating including ion implantation, ion beam assisted deposition. We can go for roughening or etching. Roughening is also known as etching. So it can be done by plasma etching or any mechanical roughening, like if you use various abrasives. Then patterning involve lithography, direct writing, self-assembly, and 3D patterning. Apart from that, coating as we discussed, like polymer coating, solvent coating, plasma spray, grafting, like plasma grafting, radio grafting, photo grafting, and multi-layer films involving like biological methods like biomacromolecules. Like if we coat the if we coat the biomaterial with various lipids or proteins, so we can these particular methods are few of the methods to modify the surfaces. So we can discuss one by one. So various modification routes involve these physical, biological or chemical routes. So in case of physical modification, various techniques like physical vapor depositions or evaporation, that includes evaporation, sputtering or plasma arc spraying over the biomaterial. Then there is electrodeposition also, 3D printing, again roughening and etching. So one by one we can discuss few of these. Uh, these are various chemical modifications as well as biological modification. So in case of biological modification, as I said, that we can coat biomacromolecules including proteins, nucleic acids, lipids, and carbohydrates. So a biological modification, there is a physical adsorption of these biomacromolecule over the biomaterial. So various approaches like immobilization, cross-linking, and conjugation are part of it. Okay, so plasma spraying is one of the physical methods. So what we do is, this is basically a cathodic arc deposition. So arc plasma spraying process occurs at atmospheric pressure, or even vacuum plasma spraying or low pressure plasma spraying. Right. So we spray the high melting point materials like titanium, stainless steel, or tungsten. These kind of high melting point materials are used. So in case of spraying, we use various non-reactive plasma gas like nitrogen, argon, helium, and hydrogen. So in case of sputtering deposition, again we have this target and a target holder. So the target will consist of like any hydroxyapatite. Suppose hydroxyapatite, and the substrate or the substrate holder. Substrate will be your titanium, right? So what happens is, this occurs in a low vacuum, that is 0.07 to 16 Pascal, in presence of an inert gas like argon. So a high voltage of around 1 to 5 kilovolt is applied between the target and the substrate, and these get ionized. Ionized inert gas atoms form a plasma cloud. So this is also known as magnetron sputtering. That is that it increases the plasma density by introducing a magnetic field. Fine. So there is again electrophoretic deposition. So this is also one of the physical methods of surface modification. In this case, we suspend the particle in the solution that get charged due to the applied electric field. Then again, these charged applied particles get collected on one end of the electrode and form a coherent deposition of similar shape levied by the electrode. Right, we have two electrodes here. One is the cathode and the anode, and in between that the suspension is placed. So the charged particles will get collected on one of the electrodes. Again, etching or roughening. So it can include various wet and dry etching techniques, physical or chemical etching techniques, right? So sandblasting, emery or abrasive paper, as I said, mechanical etching includes these use of abrasive papers. Physical etching includes like ion beam etching or sputter or ion etching. Again, reactive ion etching is also a way for roughening the surface. So chemical vapor deposition, it is a chemical method wherein a gas reacts with the heated substrate surface to give a solid coating, and gaseous byproducts are again removed continuously. So the coating thickness of around 5 to 10 micrometer can be obtained, and the temperature ranges at which this deposition occurs is around 300 to 900 degrees Celsius. So it occurs in three steps. So firstly, there is a transport of adducts, or that is the gas phase material, to the surface region. Then there is a surface of the gas phase reaction, and lastly, transport of the bioproducts away from the surface. So self-assembled monolayers, this is a part of again chemical surface modification technique, wherein SAMs are formed spontaneously by the interaction of the molecular constituents from solution or gas phase onto the substrate. So it consists of one chemical group which binds spontaneously to the surface, and an organic rest group, that is R. So in the figure you can see there is a S group that binds to the surface, and there is a organic rest group R. Again, polymer grafting. So there is two steps of these polymer grafting. One is the grafting to and grafting from. So in case of grafting to, there is the covalent attachment of the polymers end, whereas in case of grafting from, the polymerization initiation for growing chain occurs. So you can distinguish both these steps from the figure given just right next to it. So in case of grafting to, there will be a covalent attachment of the polymers end. So again, in case of grafting from, polymerization initiation will occur for the growing of the chains. So polymer grafting, as I already we discussed, like polymer brush coatings. So polymer brush coatings is basically done by polymer grafting, right? So moving on, what are the key challenges for the surface modification of biomaterial? So in case of physical methods, what happens is there's this short aging time, that is it has a poor stability. Also it is very expensive, and there is non-uniform surface modification. In case of biological methods, again it is a very expensive method, and it leads to poor stability of the modified surfaces. In case of chemical methods, it shows excellent stability. It is low in cost, that it is cost effective, and also it is easier to perform. So among the all three methods of surface modification, chemical methods are favored usually. So in the last lecture, that is lecture number 21, we discuss about the coating of these calcium phosphate on titanium. So what is this calcium phosphate? It is a main mineral found in the human bone and teeth, and it is usually highly biocompatible in organic materials. So in most of the bone and teeth implants, we use this calcium phosphates. So in two ways we can use this calcium phosphate. One is the hydroxyapatite, that is HA, and it has these uh, Ca10PO4 to the whole 6 OH twice molecule. As so this hydroxyapatite is hexagonal in structure and has a stoichiometry ratio of calcium by phosphate of 1.67. Other than that, we can use this calcium phosphate as tricalcium phosphate, that is TCP. So beta TCP is stable at room temperature, and it is commonly used as a degradable bone graft substitute. So if you want to use the bone graft implant as degradable in nature, we use this tricalcium phosphate. So it degrades faster than hydroxyapatite. So if we if we want the function of the implant to be degradable in nature, or if we want the properties of the implant to be degradable, we will use this mostly this tricalcium phosphate is used instead of hydroxyapatite. So a mixture of hydroxyapatite and beta TCP is known as biphasic calcium phosphate, that is BCP, and is mostly used for bone replacement. So we'll see various methods by which, or various methods by which we do this BCP films coating on titanium. So coating of BCP films on titanium. So deposition using again RF magnetron sputtering. wherein the target is placed and the substrate, that is the titania, at one end. So the target to substrate distance is around 5 centimeter, and the RF power is being supplied of 30 watts. So the sputtering gas used is pure argon at a pressure of vacuum pressure of 3 into 10 power minus 2 millibar, and the deposition time ranges from 4, 6 and 8 hours. So the more is the deposition time, the more will be the thickness of the coating. Right. So the coating thickness, that is the film thickness, is increased linearly with the time of deposition. So as you can see from the graph, between coating thickness and deposition time, as the time deposition time increases, that is at around 8 hours, there is the coating thickness of around 1000 or 1000 of around 1000 nanometer coating thickness. So at around 4 hours of deposition time, the coating thickness remains at 400 to 500, between 400 to 500 nanometer in range. So the composition of BCP here is 44 weight percent of hydroxyapatite and 56 weight percent of beta TCP, that is tricalcium phosphate. So again, if we want to compare this surface roughness and wettability in case of, with film thickness, so as the film thickness increases, you can see the surface roughness also increases. Whereas in case of the contact angle, so as the film thickness increases, so the contact angle decreases. So it becomes more hydrophilic in nature, right? So the coating contact angle at uncoated, in case of uncoated calcium phosphate or BCP, in case of uncoated surfaces, the contact angle is around 120 degrees, whereas in case of like coated surfaces, we have the contact angle of around 60 degrees, right? So the film thickness, as it increases, the contact angle decreases. So you need to remember, with increasing the film thickness or with increasing the deposition time, the surface roughness gradually enhances and the contact angle decreases. Similarly, in case of we can go for laser cladding of these hydroxyapatite and functionally graded titanium precursors, titanium oxide HA precursors on titanium. So these precursors consist of 100% of HA and functionally graded TiO2 HA material. So you can see two kind of surface modification. One is the titania and HA, and another is the FGM and titania. So in case of FGM, it consists of these 5 layers, that is 100% titanium oxide, again 25% HA plus 75% TiO2 and so on. So what we do is, again the substrate titania is kept on one end, and laser cladding or through laser beam, these cladding or surface modification occurs. So pulsed layer of ND-YAG, that is neodymium doped yttrium aluminium garnet, is used. So laser power and wavelength is at around 500 watt and 1.064 micrometer respectively, and the laser energy density is of around 21.6 joule per millimeter square. So inert gas used here is argon at 0.2 megapascals, and the scanning speed is of 4 millimeter per second. So if we see the wettability and surface roughness in this case, in case of laser cladded, that is HA cladding and FGM cladding, the uncoated surface has the contact angle of around 91.9 degrees, whereas in case of 100% HA cladded surface has contact angle of 71.3 and FGM cladding has 60.6. So you can see that the contact angle gradually decreases with these surface modifications. The roughness factor, that is the RA, also in case of non-cladded titania is 0.99, which is lesser. In case of FGM is 3.57, and in case of HA cladding it is 5.16. So as the modification changes, the surface roughness increases. Whereas other than that, in case of protein adsorption also, so the protein adsorption in case of FGM is the highest, whereas in case of titania is the lowest, right? It is around 4 microgram per centimeter square in case of FGM modified surfaces. So cladding result in higher amount of absorbed mass of protein, and higher amount of these adsorbed protein mass on FGM attributes to surface composition. Again, the roughness factor you can see it decreases. It is the least in case of titania, whereas in case of 100% hydroxyapatite modified surface, it is the highest, that is 5.2 micrometer. Similarly, you can study the cell adhesion. So cell adhesion in case of human osteoblast Mg63 cell lines were cultured in DMEM at 37 degrees Celsius in a 5% CO2 for 12 hours. So cladded samples exhibited better affinity. How can you study that? We can go for studying the nuclei structure. We can go for determining the rate of the area of the surface area for the cell adhesion available. So herein the cell adhesion percentage has been determined, and the graph between this percentage of cells adhered and contact angle, you can see that the FGM coated surface has the highest percent of cells adhered, whereas in case of titania it is the least. Similarly, the nuclei area in case of the FGM coated surface is the highest, whereas again in case of titania it is the least. Circularity also is studied. So the circularity increases in case of titania, and in case of FGM it is the least one. So, so the coating of these PCP TiO2 films on titania by RF sputtering can also be done. So BCP titanium oxide, that is three different compositions such as 100% BCP, then 25% titanium oxide and 75% BCP, or 50% titanium oxide and 50% BCPs can be fabricated using again RF magnetron sputtering. So these sputtering power ranges between the 40 watt for 7 hour, and sputtered samples are annealed at 700 degrees Celsius for 2 hour. So in this case, it was found that the coating thickness was the highest in case of titanium oxide 50% and 50% BCP, that is 1320 plus minus 56 nanometer. Whereas in case of 100% BCP coated surface, it was 540 nanometer. So you can see the difference in the coating thickness depends upon the composition of the modifying surfaces, right? So similarly, the contact angle can also be studied. So this contact angle, as you can be like you can compare this using the Wenzel equation. So the decrease in the contact angle will occur with the increase in the roughness. That is, Wenzel equation is actually given by cos theta is equal to RF cos theta naught. So RF is the roughness factor. Similarly, protein adsorption can be studied when compared with the contact angle and the roughness factor. So you can see here that 1 denotes BCP, whereas 2 denotes 25% and 25% titanium oxide and BCP, and 3 denotes the 50% titanium oxide and 50% BCP. So in this case, you can see the protein adsorption is highest in case of 1, that is the 100% BCP modified surface. Also, the contact angle is highest in case of these 100% BCP coated surface. Whereas the roughness factor is the highest in case of titanium oxide. So this does not kind of favors the usual what do we say, the the usual results in case of the roughness factor. So hydrophobicity plays like a major role in case of determining this protein adsorption. Right. Similarly, cell adhesion can be also studied by determining the percentage of cell adhered and contact angle. Similarly, the nucleus area, as we already studied the nucleus area, determining the nucleus area helps in determining the cell adhesion. So you can see various modified surfaces as well as uncoated surfaces are compared here. So this wraps your lecture 21 content, and the lecture 21 was basically the comparison. How can you compare between various coating surfaces or surface modified surfaces, right? So now we will go into uh, discussing various questions that will again help you to solve the questions of the week 7 course content. So the first question you have is, which of the following is not a purpose for surface modification in case of biointerface engineering? So your options are here. A is to change the biomaterial crystal structure. B, to reduce the undesirable adhesion or reactions. C is to enhance the biomaterial specificity towards the particular cells. And D is to tune the biointerfacial interaction. So you have to basically select one of these options which is not a purpose or not a role for surface modification in case of biointerface engineering. So you have been given four options. So among these four options, one option is not a purpose of for surface modification. Okay, so I will give you like 1-2 minutes. So I hope this question you are able to understand the question, what the question is asking. So three of the options are actually correct and defines the purpose for surface modification, whereas one of this is incorrect one. Okay, so let us discuss the answer to this one. So first option is A, that is to change the biomaterial crystal structure. So Okay, so I lost my network in between. So first is to change the biomaterial crystal structure. So what do we want the modified surface to have actually an impact on the crystal structure? Do we specifically want? So no, we do not want to change the biomaterial crystal structure specifically. So why do we want this surface modification? So as you can see in the option B, to reduce the undesirable adhesion or reaction. So we do not want any pathogens or other microbes to get and adhere to the biomaterial. So we actually want to reduce these undesirable adhesion or reactions. Again, option C, that is to enhance the biomaterial specificity towards particular cells. As when a biomaterial is implanted into the body, we want it to function properly. So sometimes what we want is we want these biomaterial to be specific for a particular cell. So for that purpose, we sometimes we modify the surface of the biomaterial so that there is an enhancement in these biomaterial specificity towards the particular cells. So option number C is a purpose for surface modification, right? And option D, that is to tune the biointerfacial interaction. Again, option B and C both are actually uh, the criteria to tune or a way by which you tune the biointerfacial interaction. So all the three options B, C and D define the purpose for the surface modification in case of biointerface engineering, whereas option A, that is to change the biomaterial crystal structure, is not a purpose for surface modification, right? So your correct answer for this question is option A, that is to change the biomaterial crystal structure. Is it fine? If there is no doubt, we can go to the next question. Okay. Moving on, we have our question number second, that is, which of the following is not an approach for surface modification? Again, we discussed about various methods for modifying a surface. So options are A, that is low surface free energy coatings. B is polymer brush coatings. C is application of negatively charged surfaces. And D is positively charged surface fabrication. So you have been given four options, among which one of the option is not an approach for surface modification. So three of the options again are correct. However, one of these we do not use it for surface modification. So I will give you some time to relate to the question, and if you can possibly try to guess, you can just guess what could be the correct answer to this question. Okay, so one by one we will see. So option A, that is low surface free energy coatings. So if you want to modify the surface, what do we favor? We want the delta G of adhesion or the Gibbs free energy to be on the lower side, right? So it should be less than 0, right? So basically lower surface free energy coatings help in attaining or help in attaining the modification of the surface, right? Similarly, polymer brush coatings, various polymeric substances, when can be grafted onto the biomaterial. So in such cases, what happens that the grafting density determines the cell adhesion. So more is the grafting density, the lesser will be the cell adhesion. Third is application of negatively charged surface. So we usually go for application of positively charged surfaces, and this is because we want various hydrophobic interaction to occur. So for that, we want the electrostatic interaction to occur. So various positively charged surface fabrication result in electrostatic interaction. So these strong electrostatic interaction, what does it do is they hinder the cell elongation and even cell attachment. So ultimately, it prevents the adhesion of various pathogens and microbes onto the surface. Right. So the correct answer to this question would be option number C, that is application of negatively charged surfaces. So as you can see, surface modification approaches involve application of positively charged surfaces, low surface free energy coatings, and polymer brush coatings. So option C, that is application of negatively charged surfaces, is not an approach for surface modification. Is it fine? So you can move on to the next question if there is no doubt. So third question is, what kind of surfaces promotes the adhesion and absorption of components from solution? So you have to say like what kind of the surfaces nature promotes the adhesion of these components or adsorption of components from the solution. So options are A, hydrophobic surfaces, B, hydrophilic surfaces, C, amphiphilic surfaces, or D, none of the above. So amphiphilic surfaces are usually those surfaces which will have both hydrophobic as well as hydrophilic ends, or it is both hydrophobic and hydrophilic in nature. So I have to tell which kind of surface promotes the adhesion and adsorption. So we'll wait for some time for catching up what's the answer to this question. So what kind of surfaces promotes the adhesion and adsorption of components from solution? A, hydrophobic surfaces, B, hydrophilic surfaces, C, amphiphilic surfaces, and D, none of the above. Okay, so the correct answer would be option number. Okay, so the correct answer would be option A, that is hydrophobic surfaces. So why hydrophobic surfaces? So these hydrophobic surfaces have the main reason for this is that there is an increase in the interaction between the hydrophobic surface and the hydrophobic protein or the polymeric substance domain that become exposed during the adsorption process. So basically hydrophobic or hydrophobicity is increased and helps in the attachment of these protein and polymeric substances from the solution to get adhered into the surfaces. So basically hydrophobic surfaces promotes the adhesion and adsorption of components from solution as well as surface active substances. Again, hydrophobic surfaces also promotes the protein adsorption as well. Right. So the correct answer would be option A, that is hydrophobic surfaces. Fine. So we can move on to the next question if there is no doubt. So question number 4, deposition of cells decrease with dash grafting density of the polymer. So you have to fill up the blank here. Options are A, decreasing, B, increasing, C, exponential decrease, and D, no effect of. So deposition of cells decrease with decreasing grafting density of the polymer, or is it increasing grafting density of the polymer, or there is an exponential decrease in the grafting density of the polymer, or the deposition of the cells does not have any effect when there is a graph with the grafting density of the polymer. So you know where do we this grafting density of the polymer comes from? We studied this basically in case of polymer brush coatings, or you can say during the polymer grafting. So when we graft a polymer onto a surface, how will it affect the deposition of the cells over this modified biomaterial? So you have to answer this particularly. So your options are A, decreasing, B, increasing, C, exponential decrease, and D, no effect of. So I'll wait for 1 minute for you all to absorb the question and kind of relate to it. I already explained once. So if you want me to explain it again, I can explain the question. Okay, so what would be the correct answer? So, so the deposition of the cells decreases with increasing the grafting density of the polymer. Right. So we studied that when we graft these polymer or we have these polymer brush coatings over a surface, so the lower will the distance between any two uh, polymer, the more will be the so the lower the distance between any two polymer, so it will repel the cells to adhere to the surface. So the cell deposition will decrease, right? So the correct answer would be option B, that is increasing. So this we already discussed while going through polymer brush coatings. So various orientation of the polymer like mushroom oriented polymer, or uh, Then there was one was mushroom and another was brush like, right? Uh, Let me check it once. As you can see from this figure, yes. So in case of brush like polymer coatings, see the distance between the two polymer is less, whereas in case of mushroom like polymer brush coatings, the distance is more. So the if the grafting density increases, so the deposition of the cells will decrease. Whereas if the grafting density decreases, the cell deposition will increase. So this was what the question was asking, that you have to fill the blank space. So deposition of cell decreases with increasing grafting density of the polymer. So increased density of the polymer brush coating decreases the cell adhesion. So the more will be the polymer brush coating, the lesser will be the cell adhesion. Okay, so we can move on to the next question if there is no doubt. So question number 5 is, which of the following surface coating resists platelet adhesion? So A is fibronectin, B heparin, C alginate and D albumin. So in case of biomimicry or the biomaterial to mimic the biological function, what we do is we coat the surface with certain substances that ultimately perform various function, which is actually biological functions, right? So how can we resist the platelet adhesion? What kind of coatings do we use to resist the platelet adhesion? So A is fibronectin, B heparin, C alginate and D albumin. So you have to think about what each of these coatings have their functions. What is the function of these coatings? Like fibronectin, how does it work? Heparin, alginate and albumin. So we have to resist the platelet adhesion. So we will see one by one. So in case of fibronectin, or where do we use this fibronectin coatings or collagen coatings? And again, where do we use this heparin coating, even alginate and albumin? Can you answer? So if not, we'll see one by one. So these fibronectin or collagen is coated when we want to promote the cell adhesion, right? So in case of surface coated with fibronectin or collagen, there is the promotion of cell adhesion. Whereas if the surface is coated with heparin, it acts as an anti-thrombogenic surface. So apart from that, alginate is typically used in form of a hydrogel in case of biomedicine. So including wound healing, drug delivery and tissue engineering applications. So usually alginate in the form of hydrogel is actually acts as a ECM, that is extracellular matrix, right? So you have to remember again, surface coated with albumin, it resists platelet adhesion. So the correct answer would be option D, that is albumin. So albumin surface coatings resist the platelet adhesion, whereas fibronectin or collagen surface, when the surface coated with fibronectin or collagen, it promotes the cell adhesion. In case of heparin coated surfaces, it acts as an anti-thrombogenic surfaces, whereas alginate, if any surface is coated with alginate, it usually is used as a hydrogel or acts as a extracellular matrix. Right. So not just for albumin, any questions can be asked regarding the function of fibronectin, heparin, alginate as well. So also including albumin, you must remember all the functions of other surface coatings as well. Right. So we can move forward to the next question, that is question number 6. Again, a similar question is there. So which of the following surface coatings promotes the bone cell adhesion? So options given here are A. Collagen, B. Hydroxyapatite, C. Polyethylene oxide, and D. Albumin. So as we already saw in the last question, what albumin does is that it resists the platelet adhesion, right? So already you can rule out the option number D. So you're left with three options: collagen, hydroxyapatite, and polyethylene oxide. So you have to tell me what kind of surface coating promotes the bone cell adhesion. So in the previous question we were asked about what kind of surface coating resists the platelet adhesion. That was albumin. So herein you are asked what kind of surface coating promotes or helps in the bone cell adhesion. So can you recall all the lecture we just recap? Was very briefly discussed in, or you can say very nicely discussed in case of lecture 21 about what is this hydroxyapatite. Okay, again, so if you see option number A, that is collagen. So collagen or fibronectin, it helps in cell adhesion, right? So particularly bone cell adhesion it does not talk about, but it promotes the cell adhesion. Again, polyethylene oxide, wherein we use this PEO or polyethylene oxide. Okay, so we will see what is the correct answer to this question. So option B, that is hydroxyapatite, is your correct answer. So hydroxyapatite, that is a molecule containing calcium phosphate, is used in bone implants and it helps in promoting the bone cell adhesion, right? Whereas collagen or fibronectin, it promotes the cell adhesion. Polyethylene oxide, again, it acts as a hydrophilic surface that reduces the protein adsorption. So if you want any surface modification where you want to reduce the protein adsorption, usually we do not. However, even if you want any surface wherein you want to reduce the protein adsorption, you can coat the surface with these polyethylene oxide. So these polyethylene oxide acts as the hydrophilic surface. So as we already discussed that hydrophilic surfaces reduce the protein adsorption, whereas hydrophobic surfaces promotes or favors the protein adsorption. So again, albumin, as we discussed, that surface coated with albumin resists the platelet adhesion. So we're left with option B, that is hydroxyapatite, which is the correct answer. And hydroxyapatite coated surface promotes the bone cell adhesion. Fine. So if there is no doubt, we can move on to the next question. Question number 7. Which of the following strategy cannot be used to reduce the surface friction or wear? So surface friction or any wear and tear caused by the implant in the body. So what kind of strategy is used to reduce the surface friction? And this question asked, there's one option among these is cannot be used to reduce the surface friction or wear. So option A is hydrophilic surface modification, B is hydrogel coatings, C is polymer and protein coatings, and D is silver coatings. So we have to detect one of these option which is incorrect and cannot be used as a method to reduce the surface friction or wear caused by the implant. So already just now we discussed this option A, that is hydrophilic surface modification. If you think about the functions, what will happen if we coat each of these substances? You can easily give the answer. So we will wait for 1 minute for you to think. Then I will try to explain how can you answer this question. Okay, so hydrophilic surface modification, hydrogel coatings, polymer and protein coatings, and last is silver coatings. So you have to tell me which of these strategy cannot be used to reduce the surface friction or wear. So we will see what is the correct answer to this question. So it is option D, that is silver coatings. So why do we want to reduce the surface friction or wear? As I already discussed this, that in several cases in few of the bone or joint implants, we want high lubricity to reduce the frictions and wear. So we do not want any friction or any injury inside the body. So we want the surface to be have high lubricity or have the property of high lubricity, right? So hydrophilic modification of the surface, like using again polyethylene oxide, uh, can help the surface increase the liquid on the implant surface, which acts as a synovial fluid. So option A, that is hydrophilic surface modification, can be used to reduce the surface friction. Again, hydrogel coatings. So coatings of polymers, hydrogel and proteins can help in reducing the surface friction and wear. So option B and C both help in reducing the surface friction, right? So last option, that is option D, that is silver coatings. So usually these silver coatings or silver nanoparticle coatings are a traditional approach of surface modification, wherein these silver coatings are used as a antimicrobial agent. So antimicrobial agent means that it does not allow the microbes to deposit or adhere over the surface. So any surface coated with these silvers or silver nanoparticles will act as antimicrobial, and it won't primarily reduce the surface friction or wear. Right. So the correct option for this question number 7 is option D, that is silver coatings. All other options, that is hydrophilic surface modification, hydrogel coatings, and polymer and protein coatings, can be used to reduce the surface friction and wear. Fine. We can move on to the next question if there is no doubt. Okay. So question number 8 is, which of the following is or are the physiochemical properties of a surface? So which of the following properties define the physiochemical properties of a surface? So option A is wettability, B is texture, C is potential, and D is all of the above. So while modifying a surface, we need to basically determine the physiochemical properties. We need to keep in mind these physiochemical properties of the surface. How will it alter these properties? So which among the following is or are the physiochemical properties of a surface? A is wettability, B texture, C potential, and D all of the above. Okay, so the surface properties or the physiochemical properties of a surface includes all of the above, right? So option D, that is all of the above, is correct option. So usually these physiochemical properties of a surface involves surface wettability, that is option A. So that is defined by the contact angle of the surface, whether it is hydrophobic in nature, hydrophilic in nature, or it is neutral, right? So if the contact angle is greater than 90 degree, it is hydrophobic in nature. If the contact angle is less than 90 degree, it is hydrophilic in nature, right? Again, surface texture. So surface texture involving the composition or the roughness factor. So the roughness factor of the surface determines the surface texture, or surface roughness is given by the roughness factor. It is by the Wenzel equation. Whereas the surface texture, again, what kind of texture does the surface have? What kind of properties does it have? Then there is option C, that is potential. So surface potential. So what kind of charges are present on the surface? Right. What is the surface potential? So all of the above, that is A, B and C, all of this includes the physiochemical properties of a surface. So apart from that, we have surface chemistry as well as surface roughness also, that defines the physiochemical properties of a surface. So surface chemistry, as in what is the composition and what kind of chemical nature of the surface is, and surface roughness, as I said, it is given by the Wenzel equation. So how rough or how smooth the surface is. So these physiochemical properties of a surface are the aspects that needs to be taken care of while modifying a surface, right? So if there is no question, no doubt, or is this question understandable, so we can move forward to the next question. So okay, question number 9. So question number 9 is, which of the following methods is or are used for surface modification? So you have to tell that which of these following methods are the methods that is used for modifying a surface. A is chemical vapor deposition, B electrodeposition, C biomacromolecules coating, and D is all of the above. So it is a easy question kind of, and also we discussed all of these during the recap of the lectures. So which of the following methods is or are used for surface modification? How can we modify a surface? So can we go for chemical vapor deposition? Can we go for electrodeposition? Or can we go for biomacromolecules coating? Or all of these above methods are ultimately used for surface modification? So you can try to give the answer uh, even if you don't know. I'm obviously going to discuss the answers. You can wait for 1 minute, then we will move forward. It's been continuous stretching of the session, so we can have a 2 minutes break before we move forward and give the discuss the answer to this question. Right? Okay, so which of the following method is used for surface modification? So as you can see, all these three options, as we discussed, are used for surface modification, right? So depositing a surface with chemical vapors can modify the surface. Deposition of various or sputtering using sputtering and electrodeposition can also modify the surface. Again, biomicromolecules coating involving coating of the surface using lipids, proteins, carbohydrates, or even other peptides as well can modify the surface, right? So the correct answer for this question would be option D, that is all of the above, right? So as you can see, option A, that is chemical vapor deposition, is a chemical method, whereas option B is electrodeposition. It is a physical method of surface modification, whereas option C, that is biomacromolecules coating, it is a biological method for surface modification. So all these biomacromolecules coating on the surface occurs through various physical approaches only, right? Physical contact method like immobilization, or even physical adsorption like immobilization, then cross-linking, or even conjugation. So the correct answer for this question is option B, that is all of the above, right? So if there is no doubt, we can then move on to the next question. So okay, we have question 10, that is, which of the following methods is not a chemical surface modification method? Just now we discussed that one among them was chemical method, another was physical and biological method. So herein you are given four options, among which one of these is not a chemical surface modification method. So you have to remember the term chemical surface modification, and one of them is not a chemical surface modification method. So options here are A, thiolization, B, etching, C is polymer coating, and D is silanization. So can you recall what are these thiolization, etching, polymer coating, and silanization are? Okay, so I'll wait for 1 minute, then we will try to discuss the answer to the question. So which of the following method is not a chemical surface modification method, right? So what do we do in thiolization and silanization? What are these terms basically meant as? So in case of thiolization, what do we do is we coat the surface with substance that contains thiol containing substances, or the thiol group, right? So any substance containing this thiol group, when coated onto a surface, we call it as thiolization. Silanization is coating of silica gels, or any silica containing compound. When there is a coating of this silica containing compounds, it is termed as silanization. So both this thiolization and silanization are actually chemical surface modification methods. So what are we doing is we are chemically modifying the surface. We are using this chemical substances to modify the surface, right? Similarly, if you see option C, that is polymer coating. So coating of any polymer, any surface active substance, right, over the surface is basically modifying the surface. So this is also any chemical or any polymer like alkali polymer or any other plant-based polymer, right? So coating of any polymer will actually modify the surface, and this is also a chemical route of surface modification. So your option A, that is thiolization, option C, that is polymer coating, and option D, that is silanization, are all a method for chemical surface modification. Whereas option B, that is etching. So etching is another name for roughening. So roughening or etching, so this is particularly not a chemical modification method for surface modification, whereas it is a physical method, right? So etching is a physical method for modification of surfaces. So as you can see, chemical modifications of methods involve chemical vapor deposition, self-assembled monolayers, that is salinization or thiolization, immobilization, then acid or alkali treatment, and polymer coating. So all these methods are chemical surface modification method, whereas etching or roughening. So roughening or etching may also involve plasma ion etching or reactive ion etching. So these particular techniques are actually physical method for surface modification and not a chemical surface modification. So the correct answer for question number 10 is option B, that is etching, right? So is there any doubt? So if not, we will move forward to the next question. Question number 11. So again, we have a similar question. So which of the following method is a biological surface modification method? Right. So options here given as A, self-assembled monolayers, B, cross-linking, C, conjugation, and D, coating of lipids. So actually, this question should be which of the following methods is not a biological surface modification method, right? So let me just change it. So there is a mistake in this question. Okay. So which of the following method is not a biological surface modification method? So options are self-assembled monolayers, cross-linking, conjugation, or coating of lipids. Um, so just now we went through chemical modification method, if you recall. So in that case, it was given this option for self-assembled monolayers, right? So self-assembled monolayers involving thiolization or salinization comes under chemical surface modification method. So your correct answer would be option A, right? And all the other option, that is cross-linking, conjugation, this is the adsorption methods by which any biomacromolecule attaches to the surface. Whereas this coating of lipids, coating of any kind of biomacromolecules like coating of lipids, proteins, peptides, carbohydrates are all biological surface modification methods. So, self-assembled monolayers is not a biological surface modification method, right? So, option A is your correct answer, that is self-assembled monolayers. It is a chemical surface modification method and not a biological surface modification method. So, we can move on to the next question if there is no doubt. And you have to again remember, as I said, it was a mistake from my end as well, that the question read as uh, yeah, method is a biological surface modification method, whereas it should be read as which of the following method is not a biological surface modification method, right? All the three options B, C, and D, cross-linking, conjugation, Again, immobilization is a physical adsorption method through which this biological modification takes place. Coating of biomacromolecule involving protein, peptides, peptoids, nucleic acids, lipids, and carbohydrates all come under biological modification techniques. Right? So we can move forward to the next question if there is no doubt. So you have your question number 12, which is which of the following methods is a method of etching or roughening? So we already discussed this etching or roughening. So it is a physical method for surface modification, right? And you have to determine again which of the following methods is a method for etching or roughening. So A is sandblasting, B is emery or abrasive paper, C is reactive ion etching, and D is all of the above. So you have to see etching or roughening can be done by sandblasting, or is it done by using emery or abrasive paper, or is it done by reactive ion etching, or all of these three options are correct. Okay. So what was this etching or roughening used for actually? So roughening or etching a surface, what it does is it creates a hydrophobic surface. So any super hydrophobic surface or any hydrophobic surface, it does not allow the particles to easily adhere onto the surface, right? So we do not want this any kind of pathogens or any other microbes that are undesirable to adhere onto the surface. For that we do, or we modify the surface by etching or roughening. So this is a physical technique and it involves basically all these above options. That is, it can be done by using sandblasting, using abrasive paper or emery, like it is a mechanical way of roughening, then again reactive ion etching. So the correct answer to this question would be option D, that is all of the above. So etching or roughening again involves, other than these three options, it can also use ion beam etching or sputter or ion etching, that is plasma etching, right? So not just these options, any other plasma etching or ion beam etching should be also remembered, right? So etching or roughening, it can be either be done using dry or wet gas, then physical methods of abrasive paper, that is mechanical method of using abrasive paper, chemically, then again reactive ion etching can be done. So all these methods are physical in nature. So the correct answer for this question is all of the above. That is, etching or roughening involves sandblasting, emery or abrasive paper, and reactive ion etching. So if there is no doubt, we can go forward and discuss the next question. So question number 13 is which of the following is true for polymer grafting from? Right. So polymer grafting can be it either polymer grafting to or polymer grafting from. So which of the following statements is true or indicates what is this grafting from term? Right, so option A is polymerization initiation for growing chain. B is covalent attachment of the polymer's end. C is chemical binding to the surface, and D is none of the above. So you have to recall what is this polymer grafting is, wherein we use polymer brush coatings, and how does it occurs. So there are basically two steps, that is one is polymer grafting to and another is grafting from. So what does these two terms, that is grafting to and grafting from, basically means, and then you can give the answer. So options are A, polymerization initiation for growing chain, B, covalent attachment of the polymer's end, C is chemical binding to the surface, and D is none of the above. So you can think of it as like what was actually the steps involved in polymer grafting, right? So you can wait for 1 minute for you all to absorb the question, and till then try to think about what could be the answer, and then we can discuss. Okay, so option A, that is polymerization or initiation for growing chain, uh, is actually the correct answer, that is grafting from. So grafting to is basically the covalent attachment of the polymer's end towards the surface, whereas grafting from is the polymerization initiation for growing chain. So firstly, there will be the covalent attachment of the polymer's end into the surface, and then the next step would involve the polymerization of these chain, or polymerization initiation for the growing chain, so that the polymer will grow and create a orientation, either it is brush like orientation or a mushroom like orientation, right? Whereas chemical binding to the surface is not an appropriate answer, and also D, that is none of the above. So the correct answer for this question is actually option A, that is polymerization initiation for the growing chain. And you can just see from this particular figure what is this grafting from and grafting to basically is. So grafting to is covalent attachment of the polymers, and as you can see, various polymers are getting attached onto the surface, and again there is a block attachment site as well, whereas grafting from is polymerization initiation for growing chain. So think of it as once the polymer end has been grafted onto the surface, the surface then um, with the in, increases in and sorry increases the or elongates its chain, right? Elongates its polymer. So you can see there is a surface initiator first, which gets attached to the surface. So various monomers one by one they attach to the surface, and lastly it it is it becomes into a polymer, right? So grafting from is actually polymerization initiation for the growing chain. Fine. If this question is understandable and if there is no doubt, we can move on to next question. So we have two more. Sorry. So we are left with two more questions. Hello. So let's move on to the question number 14, which is which of the following is or are the key challenges for physical surface modifications? So you have to think about what the key challenges are specifically for physical surface modification when you go for physical methods for modification of the surfaces. So A is poor stability, B is expensive, C non-uniform surface modification, and D all of the above. So you have to tell that which one of the following is or are the key challenges for physical surface modifications, right? So if you think about when we go for physical surface modification, usually what it does involves it's like electrodeposition, that is sputtering, or even plasma arc spraying. So such kind of methods are usually quite expensive, right? Again, there is immobilization or even UV treatment. So these particular modification are expensive in nature. Most of these approaches or methods used are expensive in nature. So you can just rule out option B as of now. Also, it has been seen that when we do these physical modification, so it results in a non-uniform surface modification. So basically, if if there is a non-uniform surface modification, there will again be poor stability, right? So poor functionality or the poor stability of the modified surface. So correct answer for this question would be option number D, that is all of the above. So when we look into the challenges faced for physical methods of surface modification, so short aging time, that is poor stability, again it is expensive, as well as non-uniform surface modification is seen. So the correct answer would be option D, that is all of the above. Apart from this, if you see the key challenges during biological methods, so these are expensive also, as well as there is a poor stability, right? So what happens is sometimes also what it is inefficient, like for various cells if you try to modify the surfaces, so the cell could not get adhere, or there is uneven coating of the biomicromolecules, or the conjugation does not happen properly. So what will it lead to? It will lead to the poor stability of the modified surface. Whereas in case of chemical methods, usually it is cost effective and it is easier to perform, as well as there is an excellent stability because the uniform surface modification is present. Right. So not just for physical surface modification, you must remember key challenges for biological as well as chemical methods, so that any other questions pertaining to these methods, if asked, can be also answered easily. Right. So the answer for question number 14 is all of the above. That is, for physical surface modification, the key challenges faced are poor stability, expensive in nature, as well as there is non-uniform surface modification. Okay, so we can move on to the next question if there is no doubt. This is the last question for today's session. It is, which of the following is true when coating thickness is increased? Usually what happens when there is a thickness of the coating is increased, what happens to the surface roughness and contact angle? So options here are: A is surface roughness increases and contact angle decreases. B is surface roughness decreases and contact angle increases. Option C is both the surface roughness as well as contact angle increases, whereas option D is surface roughness as well as contact angle decreases. So you have to think, then when the coating over the surface is increased, so when the deposition time is increased, usually what happens, the thickness of the coating is eventually increased. And when these coating thickness is increased, what will it, how will it affect the surface roughness and the contact angle? So this is the last
So this is
question.
the last question.
So this is the last question for today's session. That is, which among the following is true when coating thickness is increased? So options here are: A, surface roughness increases and contact angle decreases. B is surface roughness decreases and contact angle increases. C, surface roughness and contact angle, both of them increase. Or D, is it surface roughness and contact angle, both of them decreases. So we'll look into the answer. If you can recall, what happens when the surface, the coating thickness is increased. So usually what happens is the surface roughness increases and the contact angle decreases. So this can be analyzed or this can be determined using this following graphs. So as you can see from the first graph, which is actually surface roughness versus the film thickness. So you can see uncoated material, the surface roughness is the least, whereas as the film thickness increases or the coating in the surface increases, we have this surface roughness that is around 160 nanometer. So as the film thickness or the surface thickness increases, so the surface roughness increases, right? Whereas if you plot a graph between the contact angle and film thickness, you can see in case of uncoated, the contact angle is the highest, whereas as the thickness of the coating increased, the contact angle has decreased. So when the film thickness is around 1000 nanometer, so the contact angle is around 60 degrees, right? So you can say that when the coating thickness of any surface coating is increased, the surface roughness gradually enhances and the contact angle decreases. Henceforth, the correct answer for this question was option A, that is surface roughness increases and the contact angle decreases when the coating thickness is increased. Is it understandable? Did you get the question as well as the answer? So we will wrap up the session as for now. So this was particularly the last question, and so we have one more session left, that is the week 8 course content recap as well as discussion for the assignment questions. That will again happen in the next week, Tuesday, again from 7 p.m. to 9 p.m. So kindly follow the time, that is 7 p.m. to 9 p.m. So you can just access the live session during that period of time, 7 p.m. to 9 p.m. next Tuesday, right? That will be the last session. Yes. So let's wrap up this session. We will meet in the next session, right? You all can leave now. Thank you.